Hello and welcome to Miss Ma's Advanced Functions class. This is 1.6 Piecewise Functions. Okay, so you've probably actually seen a lot of piecewise functions but never heard the term before. A piecewise function is a function that is defined using two or more rules on two or more intervals. So we could have something that looks like, let's say I've got this line here and then I suddenly got a parabola and then another line. So this could be a piecewise function because we've got three different parts, right? And they're defined by different equations depending on what part of the graph that you're looking at, right? So that's a piecewise function. So we're going to do an example here. This is an example with different rules for different situations. A city parking lot uses the following rules to calculate parking fees. You got a $5 rate, like flat rate, for time up to and including the first hour, flat rate of $12.50 for any amount of time over 1 hour and up to including 2 hours, and then $13 plus $3 per hour for each hour after two hours. So actually it doesn't say to write the equation, but I want to write the equation for this just to show you how. The first thing we want to do is define the variables. So let x be the number of hours parked, and we're going to let f of x be the cost. And the way you write a piecewise function is you'd write f of x equals, and then you write this big curly bracket, and we're going to use the three rules, so $5, and this happens for x less than equal to 1, but we actually do need a lower bound here because in this case we're doing a real life application, and you don't want to park at a parking lot for negative amount of hours, and actually you wouldn't pay somebody to park for 0 hours, so 0 is less than x, not included because we wouldn't pay them. And then we've got $12.50 for the next interval, so that's the next rule, right? A flat rate means that we just have the constant, and we're doing 1 less than x less than including 2. And then our final rule, $13 plus the flat rate of $3 per hour for any hours over 2 hours. So x minus 2 right there. That's anything over 2 hours. So that's for x greater than 2. Right? So that's our equation. It's got the rule part, and then it's got the interval part. So which rule do we follow for which interval? And it describes it for us, okay? So let's graph that then. I've already made my graph here, and I've gone by 1s for the hours, and then I went up by 2s for the cost. And by the way, you can see that I went 2, 4, 6, 8, 10, and I don't have to label every single little square. That's a lot of work. Okay, so we're going to draw in the first one. So it's $5 and it's a flat line. It's just 5 because it's a flat rate. So it starts at 0 and it will go across to the 1. And then we're going to draw in the end points because we want to show that we are not including the 0. So make a big empty dot there. But we are including the 1. So you fill in that dot there. Okay? For 1 to 2 hours, so for this section here, we know that it's $12.50. So we will draw the $12.50 line, and actually I'm having difficulty with my software, so excuse me if this is not quite at $12.50. I think it kind of goes, oh, actually it was nice and flat, that's good. And so $12.50 from 1 to 2 hours, and I'll draw my empty dot here because I'm not including the 1 hour, and I am including the 2 hours, so a big closed dot there. And then we're going to draw the final bit. So whenever you have something that's off in the distance and it's difficult to draw this because you're not really quite sure where it goes, you could actually draw it from 0 or wherever is convenient, and then erase the part that you don't need. So if I'm thinking about this 13 plus 3x minus 2, maybe it's easier just to make it in mx plus b form. So I'll write 13 plus 3x minus 6, which is really 3x plus 7. So I'm going to draw 3x plus 7, and I'm going to erase out the parts that I don't need. So let's see. 13 is about where is that? It's about here, right? And oh sorry, I need 7. So 7 is about here, and I'm going to go up by 3s. So I should get from 1 to 10 there, 110 goes through there, and then you just can continue onwards, like that. Okay, and I'm only going to use the parts that are from 2 and up. So I'm going to redraw that line right there and erase the part that I don't need. Okay, so if you have a pencil and eraser, it's much easier, but I just have to do it with my computer. So there, I erased the part of the line that I don't want, and I'm going to just draw the empty dot on top there. So it starts right there and it goes onwards, okay? If you're having difficulty figuring out what exactly that line should look like, draw in the whole thing and then erase the parts that you don't need, because we know we only want from x greater than 2. Okay, so that's what the graph looks like, and you can see what the domain and the range are going to look like. So, oh, by the way, I just wanted a side note that if I do have 2 on top of each other and they're both colored in, guess what? This is not a piecewise function. Why not? Well, because if I use my vertical line test, I've got 2 points that touch the vertical line. Whoops. So I don't want to do that. I want to make sure that it is not filled in so that I only have 1 value for every single point. So if you have 0 less than x less than equal to 1, you don't want to add that little equal sign in both of these intervals. You want to make sure that one of them is just an inequality and not with an equal sign. Okay? So anyways, let's talk about the domain. So the domain of this, we can just look at it. It starts at 0 but is not included, and it is continuous, right? We've got all the points in between. So, you know, we could have 2.5 or 2.4 or 0.8 or something like that. So the domain is x in R, since it's continuous, such that 0 is less than x, because we've defined it like off into infinity, x greater than 2, anything greater than 2. But we can't do it at 0, and it has everything in between. Anywhere that you want to go, you can see exactly where you want to pick out the point. The range, however, is a little bit more complicated because it's continuous in some places and then it's discrete in other cases. And discrete means it's separated, right? There's no touching there. It's not continuous. So it is continuous for some of it, so I'm going to still write y in R, and I can see that I've only got, it's at 5 here, so I'm just going to put 5, comma, and then this 12.5 area, and I know that this is 13 and it's not included, but it's greater than 13, so also, you know, x greater than 13. And that is the range. So we could have partly list and also partly a set. Okay? Last, it asks us to find f of 3, f of 0.4, and f of 1. So all you have to do is look at the graph and say, okay, f of 3, look at the graph and find the answer. It's actually supposed to be on that, I think. So it's about what is this, 16. So f of 3 is 16. And f of 0.4, you could use the graph. However, I just want to point out that you can also use this function. If I'm trying to find f of 0.4 in this function, it doesn't have 3 answers, okay? Just like this one, it should only have 1 answer. If you have 3 answers, it's not a function. If it should only have 1 answer in order to be a function. So you have to think about what interval is it applied to and then which rule am I going to use. So for f of 0.4, it's between 0 and 1. That means I'm going to use this rule. So f of 0.4 is, using this rule, it's 5. And f of 1, if you look at this, you can see, okay, 1 is the endpoint here. So f of 1 also follows the same rule. F of 1 is equal to 5. When you look at the graph, it might be confusing because you've got the open and the closed, but because the open is open, you know this is not the answer, and this must be the answer. So it's consistent from the equation to the graph. Okay? Okay, so let's look at example B. It says sketch f of x equals x squared if x is less than 2 and 2x plus 3 if x is greater than or equal to 2. This is just another way to write it. I sometimes will write the comma and sometimes I'll write the if. It's up to you really. It means the same thing. So we're just going to draw the x squared, and we only want to draw it from anything below 2, so anything over here. If it's difficult for you to draw it, let's say it had asked us to draw it over here, you could still draw it and then erase it. So it's, as long as you erase the parts you don't need after you're done, that's okay. So I'm just going to draw x squared in up until the 2, and actually I'm going to make that a open dot because I don't want it to be included because this says less than 2. And then 2x plus 3 if x is greater than or equal to 2. That looks like, let's see, it's going to start at 3 and then it's going to go up by 2's like this. So when I get to 2 it's going to be right here. So I'll start with 7 and I will go up by 2's until I can't go anymore. And we need a closed dot right there. Another way to do it is just to write the x equals 2 into this equation so I can see where the endpoint is. So if I had written 2 times 2 plus 3, I would see that that was 7, and I would know that that's 2, 7 is the starting point of my graph right here. Don't forget to label it f of x, and that's it. So just graph the parts that you need, and the whole thing is called f of x. Alright, sketch and f of x equals 1 over x if x is less than or equal to 2, and 2 if x is greater than 2. So 1 over x, if you recall, looks something like it okay, first of all it goes through negative 1, 1, and 1, 1, and then it has vertical asymptotes. I do know that when I have this endpoint x less than or equal to 2, when x is 2, I know that 1 over 2 is the answer, so f of 2 is equal to 1/2. So I'm going to just draw that in there, and it is included, so I'll make the full dot. If it was not included, then I would have made an empty dot, and it just follows the vertical asymptote along here. Try to draw it in a curvy and attractive manner, and then it follows the vertical asymptote as you go along there, or sorry, horizontal asymptote, and then the vertical asymptote. I'll just draw my arrows in. And then it's 2 if x is greater than 2. So I will start at 2 and 2, and then, oh, I wanted to draw a line, and I didn't. 2 and 2, and go along it. And I need the empty dot because that is the inequality there. You could actually have both of these be inequalities with no equal sign, and it would still be a function, obviously, because then we just would not be defined at that x value. But you can't have it the other way around where they're both equal. Alright, so example D, this asks if the function is continuous. So basically what we want to do is we just want to check the ends, okay? So we're going to check for x equals 0, and we're going to check for x equals 3. We can see that because here, when x equals 2, 1 over x is 1/2, and when x equals 2 here, the answer is 2. These are not the same, but if it was continuous, then they would match up, right? So I would want them both to have exactly the same y value. So that's why I need to check the end values for both of these, and then for both of these, in order to figure out if they touch at 0 and at 3. Okay, so we're just checking the endpoints. So when we check x equals 0, we're going to check the first two because those are where they meet together. So x plus 1 is equal to 0 plus 1, which is 1. And 2x plus 1 is equal to 0 plus 1, which is 1. So because they are equal, then it is continuous at x equals 1. So far so good, it's continuous in this section. So now we want to know where this and this meet, which is at x equals 3. So I'm going to check that point right there at x equals 3. So 2x plus 1 is equal to 6 plus 1 when x equals 3, because 2 times 3 is 6. And so that adds up to 7. And then we can check 4 minus x squared, which is 4 minus 9, and that is negative 5. So since they are not equal to each other, it is not continuous at x equals 3. And that is what we call a jump discontinuity. If you drew this one, it would look something like, and I'm just going to do a very, very rough sketch, x plus 1 up till here, up to 0, and then 2x plus 1, so it sort of goes off into the distance. And then 4 minus x squared is, 4 minus x squared starts here and it goes downwards. So this is not included, and this is included, 4 minus x squared, so I was at negative 5, so it's something like this. And it shoots off, that's a parabola, into the distance. So you've got a big jump here from one to the other. That's a jump discontinuity. Okay, so this is the last question. Find the value x so that the function is continuous. As in, we want for x equals negative 1, we want kx plus 1 to equal x squared minus kx plus 2, because we want the y values to be the same, just like we just did in the last example. We want the y values to be matching. So I'm going to substitute x equals negative 1 in here. So I've got negative k plus 1 is equal to negative 1 squared minus k times negative 1 plus 2. So we can leave that one alone and just simplify this side, 1 plus k plus 2. And then we'll move, you can move the k's to the left side and the numbers to the right side, but I'm going to actually do it the other way around because it doesn't really matter. So I'm going to get 1 minus 2, which is negative 2, equals 2k, because k plus k is 2, and so k equals negative 1. And that is where this function is continuous. So that is all. Basically, we just talked about how to write a piecewise function, how to draw a piecewise function, find its domain and range. Then we talked about the continuity of piecewise functions. Thanks for watching, and I will see you in class.